What's up? What's up? Is your man Jimmy Chan. All right, so we're talking about properties of functions. So we're talking about even functions. Well, that has some symmetry about the y-axis. So here's a drawing of an even function, and if I was to take just the so-called 2 points here, what you would notice is that here I have a positive x, positive y. Where over here, what I'm going to have is the same y value, but the x value is going to be negated, okay? So the x value is going to actually be negated. So, but the same x value, just the negative of it. So here I'm trying to show if I was to plug in a negative x in for x, negative in x, in for x, I would have the same y value come out, right? So now over here with the odd function, which is symmetry about the origin, if I was to pick two points here, what will happen is that this will have both positive x and y values. However, once it has symmetry about the origin, what happens to the x? Well, that is going to become a negative x, and the y becomes a negative y. So same thing in function notation. This says if I replace the x with negative x, my result will be a negative y. Okay? So that is the difference between the even function and odd function. In other words, if you notice this, either way, I'm replacing the x with negative x. The question is, does it look like the original, or does it look like the negative of the original? So first, the given f of x, I want to find the negative of that function, and then I want to plug the x in for the negative x. All right? So of course, we would want an example. So let's say, for example, that the g of x is negative 2x to the third plus 3, right? And I want to know if it's odd or even. So first, this one right here, I know is a function. Now I want to negate that function. So I want to find negative g of x. So if I'm negating it, I'm going to negate the whole side. So I'm going to negate this. Okay. So that means the negative g of x is actually equal to 2x to the third minus 3. Okay? Great. So here is where our fight is going to be. When we plug in the x for, when we plug in the negative x in for x, and if it was to look like this function over here, then the function is actually odd. And if we plug in the x in, negative x, if we plug in the negative x in for x, and it turns out it's going to look something like this here, the original function, then we must have an even function. All right? So let's take a look. So I'm going to take this problem right here, right? And I'm going to replace the x with negative x. So I got to come over this side. I had to get rid of this x here, and I'm going to replace it with negative x. Oh, looks like I need more space here, so let me go ahead and do that. That doesn't look very neat. Negative x. Okay, so when I look at this, I have to do parentheses first, which negative x is all done. So I got to raise it to the third power. So negative x raised to the third power gives me what? It gives me negative x to the third. So now I have a negative times a negative, which gives me a positive. That gives me a 2x to the third plus 3. And that's equal to g of negative x. Okay? So now we're done. So now I want to compare. Let me do this. Let me put this in the center so I'm not playing any favorites. So the question is, does this look like this? And the question is, does this look like this? Right? So that's my actual question, right? Does it look like either one? And the answer is no, it does not, right? It doesn't look like either one. So therefore, in this case, this is going to be neither. So if it does look like this, which is close, right? It's 2x to the third minus 3, but this was plus 3. So it's not the same. And this is a minus 2x to the third. This is a positive 2x to the third. So that's why it doesn't look the same. So that's why it's neither. If it looked like this, it would have been even. If it looked like this, it would have been odd. All right? So continue on. Properties of function. Increasing function, decreasing function, constant. So constant just means that, so everything is about going from left to right on the function, right? So I'm writing everything from left to right on this function. Right? I kind of like a roller coaster, right? It goes down and then and as it goes up, it goes really slow and you hear click, 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 all the way up to the top and like, and you go down, right? So that's what the increasing and decreasing mean. Constant just means when I go from left to right, I just flatline and kind of stay consistent, right? I don't go up, I don't go down, and that's all this is saying. It's saying when you go from negative infinity to positive infinity, the y goes up. So meaning right here, I'm going down, go up. So here, let's take a look at this. So when I start, I go down. And then it goes up. And then it goes down again. Okay? So here I have no constant functions, but I can say that my increasing, or I'm increasing from negative pi halves all the way to pi halves. And notice that I'm using parentheses because right here is where we transition from increasing to decreasing, and same thing vice versa here, we're in transition from decreasing to increasing. So in those transition points, we can't say that they're increasing, decreasing, or constant. So when we're talking about this, these are always going to be open intervals. Okay? Always going to be all open intervals. So increasing is that. My decreasing, however, is actually happening in two places, right? First, it's happening over here, which, thank goodness, it ends. It stops, this is a closed circle, and it goes down to here. And then this is going to here. Now, this is a different story here. I actually would have to use a solid, so I can't even say it's always open interval, right? So I'm going to have to actually include it because that is where it starts and there's no transition point. So in this case, I actually have to say it's decreasing from negative pi to negative pi halves. Now that is a closed circle. However, let me put this back down here. Because I have two things, I actually have to play the union and then say it's the pi halves to pi. Okay? And since there's no constants, I'll leave that alone. But what's another thing that they can ask you in this graph, right? They could ask you, hey, what is the domain? Right? And the domain is going to be from negative pi to pi. What's the range? Well, its ranges is actually going to be from negative 5 to 5. The 5 doesn't look very good, so let's rewrite it. There we go. Right? So I'm going to ask for all of those things right there. All right? Heck, it could even ask for intercepts. I mean, look at this. It can even ask for intercepts, right? Intercepts, we can say, oh, look, the x-intercepts are at, what is that? Negative pi 0, and then 0, 0, and then pi 0. Right? So we could even say it that way, that we have a bunch of intercepts as well. All right? And then let's continue on to local max, min, and absolute maximins. All right, so let's take a look. So with the local max and mins, we want to make sure that we know that local max and mins usually are located in the peaks and valleys, where the global or the absolute max and mins are actually occurring. It could occur at peaks and valleys, but better yet, it exists in closed interval, so no open circles and no plus or minus infinities. All right, so if it's going towards infinity, there's no absolute max or mins. So if the highest or the lowest point on the graph is or are open circles or going towards positive and negative infinity, there are no absolute max or mins. Okay, so let's take a look at some of these. I guess I'm calling them global, so they're also known as absolute. All right, so if we look at this right here, our local max will be right here. And our local min will be right here. And the reason why they won't be our global max or absolute max and absolute min is because there is a point higher than my local max. So this will be my absolute max. And this is actually lower than my local min, so this will be my absolute min. Okay, so let's go ahead and say that. My local max here is, what is that, 8.7. My local min is 4.3. My global max is 1.8. And my global min, or my absolute min, is 11.2. There we go. All right. How about in this example here, where the points out here is not, so this point here is not higher than this point, and this point here is not any lower than this point, right? Well, if that's the case, then my local max and local min is going to be in the same place, because here is typically my local max. But since that's also the highest point, it's going to be my absolute max as well. And here is typically my local min, but since it's the lowest point, it's also my absolute min. Okay, so my local max is, that's still 87, but that's also my global max or my absolute max. My local min is a 4.3. Well, that is also my global or absolute min as well. All right. Now here, the difference is that there's a bunch of open circles. In that case, because there's no valley here, right, because it's an open circle and no peak here, I don't have a local max or local min. Now, because that I have open circles at the end, there's not really a max or a min there either. So there's no real global max or global min or absolute max or absolute min either. So that becomes an issue there. All right. All right. Now, so when we talk about average rate of change, we're also talking about slope, right? So if you think about this, slope we write as y2 minus y1 over x2 minus x1. And if I was to write that in function notation, you would tell me that that would be, oopsies, f of x sub 2 minus f of x sub 1 over x sub 2 minus x sub 1. Okay, now if you notice that these two x's here have some kind of separation between them, right? So we call this average rate of change. Okay, so remember, x2 and x1 has some kind of separation. Let's call that separation, I don't know, something small like h, right? So if you think about that, I can say this, right? So if I assume that this is x sub 1, then this x sub 2 could be my x sub 1 plus some kind of h, right? And if I was to subtract these two, what would I have left? I will have h left. Well, what does that look like? That looks like the difference quotient, doesn't it? Okay, that looks like the difference quotient. So all three of these do consider talking about slope, all right? So we gotta be careful about that. So let's say, for example, let's say f of x is equal to x squared, okay? And let's say, for example, let me see here. Let's say I want to find it where x2 is equal to, you know what? Let's play the game of 0.5 and x sub 1 is, let's go with 0. Okay, 0 and 0.5. All right, so if I was to find the average rate of change, I'll be saying, okay, f of x sub 2 minus f of x sub 1, x sub 2 minus x sub 1, so that's going to equal to f of 0.5 minus f of 0, and that's going to be over 0.5 minus 0, right? So what do I have here? Well, when I plug in 0.5 and square it, what do I have? Let's see. I'll have 0.25 minus 0, because 0 squared would be 0, over 0.5 minus 0. So I'm going to have 0.25 divided by 0.5. What the heck is that going to equal to? That's going to actually equal to 0.5. Let me double check. Because that would be 1/4 divided by 1/2, and then it will be copy, change, flip. So it's 1/4 divided by, multiplied by 2, so it'll be 2/4, so it'll be 1/2, okay? So let's take a look at what this is actually doing, okay? So let me go ahead and do this, and do this, and do this, okay? So let's see what this is actually doing, right? So I know how to graph this right here. So let's go ahead and graph that. All right, so let's say come on. Okay, however, I'm going to go a little bit big here. So I know this has 1/4, 0.5, 1/4. So let's go, let me see. Every 4 is 1. Okay, so I got this 0, 0, right? And then I have 0.5 is 1/4. That means negative 0.5 is going to be 1/4. So let me go ahead and draw that. Okay, let me see if that will work. 2, 4, 6, 2, 4, 6. Okay, that's getting better. Okay, there we go. So that works. So I actually have to focus in here, right? Actually, if I should probably make this even bigger. So really, here's my 2 points. So what am I really looking for between this point and this point? Well, what I'm really doing, actually, I probably should make this blue so that it really stands out of what I'm doing here, all right? So what is that average rate of change? So what I'm actually doing is actually I have a line right here, don't I? And what I'm looking for is actually looking at this line right here, which is called, so this right here, this blue line is called a secant line. Okay, so what I just found here of 0.5 is actually the slope of the secant line. So if I can find the slope of the secant line, that means I can find the equation of the secant line, right? Because I really have 2 points here, right? I really have 2 points here, and I have the slope. So I can actually find the equation of that secant line. So which is what I'm talking about right here, right? So I can find the equation of the secant line as long as which is a line that cuts through a non-linear graph. So I can actually bring this back up here without doing anything there. There we go. Now, to find the equation of that line, I know that this secant line, so the slope of this secant line is going to be 0.5, which is fine, or 1/2. And I had 2 points, right? I had 0, 0, and I also have 0.5, comma, 0.25. Well, the easy one would be to use is a 0, 0. So let's go ahead and do that. So I have the point slope form, which is y minus y1 is equal to m times x minus x1. So it'll be y minus 0 is equal to 1/2 times x minus 0. So the equation is going to be y equals 1/2 x. And there goes the equation of my secant line. So this is going to be the equation of the secant line. All right, and there we go. So I hope that helps. If there's any questions, please let me know. See ya. Bye.